Welcome, dynamic students. This lecture will start our exploration of rigid body kinematics in plane motion. So up until this point in this course, we've only been dealing with particles, either particles that truly are particles by dint of the fact that they are so small relative to the scale of the problem that they can be considered single points, or any body, rigid or not, treated at the center of its mass because it's undergoing translational motion, either rectilinear or curvilinear, and we don't have to be concerned with anything associated with its rotation. Now we're going to give ourselves a little bit more latitude in dealing with real problems, and so we're going to take the next step up in complexity of real bodies, and we're going to look at bodies that are rigid and that only move in a single plane. They can rotate about an axis perpendicular to that plane, but they can't move out of it. So that'll give us that will allow us to deal with a lot more realistic scenarios versus simply the center of mass that's moving. But we won't have nearly the complexity that we would with general motion, and we will not be dealing in this section with deformable bodies. We will be very much relying on the fact that a body is rigid and that our points will be moving in a certain manner relative to one another, and we'll be basing a lot of our relationships on that fact. So to kick that off, since rigid bodies are so important for this next section, what is a rigid body? So you probably heard it mentioned if you've taken statics, which probably you have, that most of the subject of statics is concerned with rigid bodies that aren't accelerating. And some mention was made of all of the points moving together, no deformation. So we're going to delve into the definition of rigidity a little bit more specifically so we can define the position and motion of points within a single body relative to each other. Okay, so the definition of a rigid body from our standpoint is a body in which the distance between each and every pair of points remains the same throughout motion. So the points are changing their position relative to a reference frame external to the body, probably an inertial reference frame if we're going to start invoking Euler's and Newton's laws. But the distance between any two points never changes in that body. So if you can think of a body being very, very stiff and not deforming, that's a natural consequence. Obviously, this is an ideal definition, but it's definitely accurate enough for most real solids. Definitely doesn't apply to fluids and viscoelastic solids and things like that that are undergoing viscous flow or something that is elastically deforming. But for most things that are fairly stiff, most structural materials, a rigid body approximation is pretty accurate. So this is useful. We can apply this more or less directly to several solid materials that we might encounter. Okay, next question. What is plane motion? It's motion in any single plane in a fixed reference frame. So we can look at that kind of thinking in terms of the concept of rigidity and say, all right, say we got a point in a rigid body and it starts at x, p, y, p, z, p. The motion can go to any x, any y, but it's got to stay with a coordinate of z sub p. It can't move out of that plane. So all the points in the body stay in the plane, and points parallel to that plane stay in the same plane that they started in. So you can think of basically everything moving in lockstep parallel to the plane of motion. Another concept that we'll think about is what's called rigid body extensions. And these are points that move with the body as if they are part of the rigid body, so they maintain their position relative to all the points in the rigid body, except they're not actually physically located on it. So the one that we'll use the most is the center axis of a pipe, a hollow cylinder. It's the center of mass if the density of the cylinder is uniform. So obviously that's going to be something we'll use a lot in rigid body motion. And it definitely moves with the pipe in this case. It doesn't change its position relative to the pipe's circumference, but it is actually attached to the pipe. So that center axis is known as what is known as a rigid body extension. So it's totally okay to use that center of mass as if it's connected to the rigid body. It will move with it in rigid body motion, not a problem. Okay, so we're going to look at a few concepts of what it means to be in planar motion, and we'll zoom in a little bit here. So we're going to look at the concept of motion versus a reference frame. So we've got a coordinate system here. So we've got our I hat moving off in this direction, J hat going vertically upward, and of course if we curl our fingers, the right hand rule says that K hat, or our Z axis, is sticking out in this direction here that I'm kind of redrawing in black. Okay, we've defined this shaded plane here as the reference plane. It's got a Z equals 0 because we've defined the reference plane as going through the Z equals 0 origin. And we're going to take a look at some point A in the reference frame. And this rigid body kind of, could be sticking out and have other points in the Z direction. And so maybe there's a point B here at another, Z equals Z1 or ZB, okay? We can think about point A as being a companion point in the reference plane to whatever point B is here, because A and B have the same X and Y coordinates. So that's the motion that we're going to be tracking. We can move anywhere in the X and Y, and so that's the motion that we'd be writing equations of motion for. B is not in the same plane, but it's going to move with A in what's effectively a reflection, of that reference plane. So it has a companion point in the reference plane. So for every point B or C lurking out here at some Z that is not in the reference plane, there is a one-to-one point in the reference frame, in the reference plane, that will reflect its motion. So you can almost think of if you've seen a shadow play where you have a screen up that the audience sees, and a light being projected from behind, presuming there isn't any kind of magnification. If you move your hand to make some kind of shape move on the screen, that shape will move in a one-to-one correspondence with your hand. So if your hand is out at point B and the reference plane is the screen, you'll see that shadow moving on the screen exactly the same way your hand is. They'll have identical motions. So that's that. Now we can say, all right, we can define a planar motion in a reference plane, allow the points in a body that are in that reference frame to move however, and we know all the other points in the body that aren't intersected by that reference frame, they're going to move in lockstep, just within their own planes parallel to that reference plane. Nothing is going to get out of its plane. So all of the Z coordinates up here, point B is gonna always retain Z sub B throughout the motion, just like A retains a Z coordinate of 0. So that's one way of thinking about planar motion, is a reference frame and then these companion points to it that move on the reference plane and represent anything off of it. Okay. As it so happens, we're very lucky because 2 points in that reference plane, if we know the location, velocity, acceleration of 2 points, just 2 points in that reference plane, we know their motion. They define the motion of the entire rigid body, because any point anywhere off that plane will have a companion point on the plane, and that point on the plane can be correlated to the position of these 2 points. So we're going to leverage that little rule to describe equations of motion for just about anything we want to find in a rigid body in planar motion. So let's take a look at this rigid body B, or script DB here. So we've defined points P1 and P2 on this rigid body, and we can define their positions relative to this reference frame F. And a reference frame is indicated by axes with little cross hatches on them, kind of indicating that that coordinate system is pinned down. So this is kind of our reference frame to which we will reference the motion of this body and maybe any other bodies. So we've got the J hat, K hat directions identified and a point O. So we can identify a position of P1 and P2 relative to that point. That's what they start with, and then we can let this body move. It's going to move from this point over to this side of the page. It translated. It moved in what looks like the J hat direction, and it looks like it rotated. It kind of flipped around. This point P kind of moved this way, and it's now at the top. So it underwent both translation and rotation. So we can now define the later position of P1 and P2 relative to that point O. But what we have found is, if I had drawn this to scale, is this distance between the 2 points hasn't changed. So that's what the rigid body definition is giving us. And each of the points will have the same motion relative to O. Okay. So another way of saying, if I know 2 points on the reference plane, I know the motion of the whole body is, well, I could also settle for 1 point and a fixed line of known orientation, which is a sneaky way of saying 2 points, because this line, to define it, you got to have another point out here. But the nice thing about a line, as opposed to 2 points, is lines are really handy for making angles. And if we can define the angle by using that line that's on the body with respect to an axis in our reference frame over here. And I'm going to switch my colors here to make it a little more visible. Oops. A little quick second here. Turn it into a dusky red, set it as default. Okay. So now I should be able to scribble in red. So if we extend the J hat axes of our reference frame, so this is like an inertial reference frame if we're going to relate acceleration to forces. So if I extend that out, our starting position has the reference plane of our body. Here we've got point P, and we've got our reference line that's fixed in the body. Hasn't moved, even though I made it look like it moved. It's parallel to J. So it starts out parallel. Then the body moves over here. And so we've translated in the J hat direction. We've moved from the middle of the page over kind of to the right-hand side. And we've rotated. So, you know, this little hook is now over here. And now our angle theta, referenced to the direction of J hat, which I've extended over here to make it easier to see, it's changed. So by looking at the position of P going from wherever it started to its new XY location, and looking at the angle change of this reference line instead of a second point, I can kind of separate moving side to side up and down, otherwise translating, versus rotating. And that rotational element that we need 2 points on a body. We couldn't do this with a single point at the center of the mass. This is the distinguishing difference between a rigid body being examined in its movement versus a body being represented by a single point at its center of mass. So we've now really laid out the differences. It's this theta, which we could really only define if we had a second point and a line. Can't do that with a center of mass. Okay, so let's take a look at the way different points move and what happens when we take a time derivative. So we can define a radius vector from some origin, some reference point in a reference frame, to a point A on a body. Now we can say it's, say, X sub a in the I hat direction and Y sub a in the J hat direction will take us from point O to point A. Great. We've developed an expression for a point on a body versus some reference frame somewhere. Could be inside the body or outside the body. We can take the first time derivative and get the velocity of that point. So now we just have X sub a I hat. We don't have to take a derivative of our unit vector this time because we've retained the unit vector directions of our reference frame. So it isn't like we've got to worry about I hat's not changing. It is the reference direction in one orthogonal direction. And we can define the same for the change of position for some b. It's going to have its own velocity. We can do the same thing with acceleration of any 2 points in the rigid body. So magnitudes are changing with time. So we're changing our position with respect to time. We're taking the second derivative to denote acceleration in these I and j directions as defined over here by our reference frame. Well, in that case, it was a jk. So this same kind of relationship will hold no matter what point we take. We will only be changing the multipliers, the magnitudes. We won't be taking any derivatives and having a non-zero derivative for time for these unit vectors because they're the same as the reference frame. Okay, so and again, this will represent the velocity and acceleration and position of any point. They will move the same. Okay, so let's use a little vector algebra and see if we can't separate that rotational element of a body from translational. So let's look at 2 points on a body again. We're going to look at 2 points and a line. Now we're going to combine the best of both. Okay. So we've got reference frame F, and we've got point of origin in that reference frame F at O here. So we've defined IJK in reference frame F, and so a positive rotation of angle theta is going to, by the right-hand rule, will be in the positive k hat direction. So if we cross I into j, we get k. So we can think of theta rotation being positive if we go counterclockwise, which is k hat. So we've got rigid body B hanging out here. We've got 2 points on the body, and we have a line connecting those 2 points. And if we take that line, we can assign a unit vector to represent the line's direction. We know how to do that. We could even get like the coordinates of P and the coordinates of Q, subtract P from Q, divide by the magnitude of the length of PQ, and voila, we got a unit vector U hat that says here's the direction of P to Q. And if we wanted a radius vector here from P to Q, we would just have the length of the distance from P to Q times that unit vector U. Okay, so we can define the location of point Q versus its origin as the vector sum of the position, the radius vector from point O to Q to P, and then add RPQ to that. So that equals ROQ. So just vector addition there. Okay, great. Let's do that. Let's write that. So we got ROQ equals ROP plus RPQ. Let's take the first time derivative and get the velocities. So we got a dot. We've taken the first time derivative. So this would be like saying VQ, first time derivative. This is like saying VP. And now we've got this time derivative of RPQ. And these should actually all be vector quantities. Didn't have our arrows on these like we could have. Okay, so how do we express the time rate of change of this vector in a way that gives us something we care about? What we'd really like to know is how fast it's moving in some direction, translating, versus how fast something's happening with this theta angle. Well, if I want to relate theta to I and j, let's use some trig. It's pretty easy. So let's just rewrite the vector PQ as its length times its unit direction. So I can write u hat as just cosine theta I plus sine theta j. So we've kind of made a relationship between this angle and the unit vectors of our reference frame, our F reference frame. And then we just multiply by the length of the vector. Okay, so it's equivalent. I can say RPQ mu hat is the same as saying RPQ cosine theta I hat plus sine theta j hat. It's the same thing by trig. Okay, let's take the first time derivative. No problem. So I dot this, take the first time derivative, and I have RPQ. Again, that length didn't change with time because it's a rigid body, and the distance between the 2 points isn't going to change. It's not stretching. If it were stretching, the distance between points P and Q would change, and in fact that would represent the extension, and is something that we would use to measure strain. So that's a mechanics of materials concept. Rigid bodies, ain't going to happen. RPQ, same all the time. It's going to move, but the distance between the 2 points won't change. But the angle might change. Let's take the first time derivative of cosine theta. We'll get negative sine theta times d theta dt, which we got over here. First time derivative of sine theta with respect to t, time derivative. We get cosine theta, and again, d theta dt, which we've factored out. Okay. So another way of writing the first time derivative of the vector from point P to point Q on a rigid body is the length of P to Q, which ain't changing with time because it's a rigid body, times the rate of change of angle theta. This line that we've established is making with time, which is how fast is the thing rotating. d theta dt, change of angle with time, is an angular velocity times this sine cosine expression. Excuse me. So we can use, this is nice, but it's a little cumbersome. It would be easier if we had something that broke theta out in terms of another vector and we didn't have all this trig traipsing along here. We can use the property of the cross product, which says that our negative sine theta I hat plus cosine theta j hat is the same as if we took the vector, unit vector k, pointing out of the page and crossed it into cosine theta I hat plus sine theta j hat. Property of the cross product. Multiply it out. You can prove it to yourself really quick. Hey, this looks really familiar. Son of a gun. That was this thing. Okay, wow. That was our u hat. That's our unit vector direction of our r from P to Q. How convenient. So I can express all of this trig in terms of our k hat vector crossed into our unit vector direction of rp to q. Okay, so let's write this out. Do some substitution. So first time derivative of rpq is the length of pq not changing with time. Angle that makes with one of the axes of our reference frame changing with time. That is changing with time. So this is our angular velocity times k hat cross mu hat. Now let's swap positions here. Let's put the angular velocity next to the k, which by the way is the direction it's pointed in. If you think about it, let's look over here. We've got P and Q, and here's a little extension parallel to our I hat direction. If we imagine this angle theta changing, this is like a rotation one way or another in the IJ plane. So as it rotates back or forth, the vector direction of that rotation is going to be in the k hat direction. So if we rearrange like this, we now are associating the vector direction of the angular velocity with the magnitude of the angular velocity. It's kind of nice because now we have what this could be called is omega, otherwise known as angular velocity, which is a vector quantity, crossed into mu hat times the scalar length of r p to q. Well, that's just the whole vector p to q. Its magnitude times its direction. Mu hat was defined as the direction of our PQ vector. So to make a long story really useful, we can define the first time derivative of our vector RPQ as the angular velocity of that rigid body, which is going to be in the k-hat direction, or in the direction of the planar normal of the plane it's moving in, crossed into the original RPQ vector. And all of that gets added to RP to get the velocity with respect to our external reference frame, or our reference frame that does not move with body B, our stationary reference frame of velocity of q. So if you got a body, it's moving some way, it's rotating with respect to a reference frame, you know the motion of one point on the body, and you want the motion of any other point, all you need to know is a radius vector from one point to the other and the angular velocity of the body. Likewise, if you know the motion, the velocity of any 2 points, and you know their position, you can get the angular velocity of the body. So this is a very, very fundamental relationship between the velocity of any 2 points on a rigid body with respect to a non-moving reference frame and the angular velocity of that body. So that's something that you will use again and again. And just to make sure we remember, we're talking about all of our velocities with respect to reference frame F. If everything was with reference frame of the body, everything would be stationary. So a little glimpse ahead to relative reference frames. So we could rewrite this theta dot k hat as omega, the vector angular velocity of B with respect to F. So that body is rotating with respect to an external reference frame. If you were standing on the body, you wouldn't feel the rotation. I'm not feeling the rotation of the Earth right now, even though I'm sitting on it. It's rotating 2 pi per day, pretty fast. Okay, so just as a quick step back, now that we've really defined rigid bodies, we've defined planar motion, and we've given an example of how to find the velocity at one point in a rigid body relative to another. We've defined angular velocity of that body relative to an external reference frame or a stationary reference frame. Let's do a quick recap of bodies versus points. So we did a lot of studies of motions of bodies via the motion of their center of mass. But in all of those cases, we were looking at position, velocity, and acceleration. We didn't see an omega anywhere in there. Even though we did have a definition of an angular velocity, it was a single point with a motion relative to an external point. It was not itself rotating. It was kind of a point. We never looked at that. So we can think of points as having a position, a velocity, and an acceleration. Bodies will have an orientation, an angular velocity, and an angular acceleration. So if you have 2 points on a body, those 2 points, if you know their positions, you will define that angle theta versus the axis of some fixed reference frame. If you know how theta moves with time, you've got angular velocity. If you know the second derivative of theta with time, you'll have angular acceleration, otherwise known as alpha. Okay, three common mistakes for using our v of 0.2 equals v of 0.1 plus the angular velocity of the body versus the external reference frame crossed into the radius vector from 0.1 to 0.2. These points P and Q have to be on the same rigid body. They're moving in lockstep. That total distance between R and P was a constant because they're on the same rigid body. So if you're working with maybe a relative reference frame system where you've got multiple rigid bodies, that is not necessarily going to be the case. So don't try to apply this with like a point Q on body 2 to a point P on body 1, or it's totally invalid and you'll get the wrong answer. So the other one is to remember that this omega, or this theta dot, is the angular velocity of the entire body. There isn't something on the body that's moving relative to the body, it's the whole body that's moving. And last but not least, this is kind of similar to our definition of moment from statics. The vector has to go from P to Q. So the radius vector in our cross product will be from the point we know to the point out here on the other side of the equation that we're trying to find. Expect to make that mistake frequently. It's okay if you end up with a sign error. That's the first place to look. So let's do an example and show how powerful this is. So we have a ladder and it's resting up against a wall and on a floor. It's going to slip. It's 30 feet long, so our L is 30 feet. The upper contact point is moving down the wall at 2 feet per second. Somebody could measure that. They're looking straight at the wall. They're going, wow, that point's sinking at 2 feet per second. How fast is point B sliding across the floor? You know, maybe somebody's standing there. Hey, that thing's going to hit your foot. You know, how fast is it moving? We might want to know what the impulse of their foot will be against it. That momentum transfer. So, as usual, we're going to follow the same steps we did in particle dynamics. So we're going to establish a coordinate system here. So we've got our I hat direction here to the right, our J hat direction going up, and that means that K is coming out of the page, and more importantly, rotation is positive in the counterclockwise direction by the right-hand rule. So a positive K hat means a positive rotation. So that's important for the sign of our theta. So next we look at, we're just in kinematics, so we're not going to be drawing an FBD yet. That's kinetics. But we're going to look at, what do we know? We know the velocity of point T. So T is that known point, is like P in that equation. B is what we don't know. So we could write an expression, the velocity at point B is equal to the velocity of T plus the rotation rate of the whole ladder. And it's not rotating about B and it's not rotating about P. And in reality, it's rotating about a point of instantaneous zero velocity somewhere out here or here. And in another section, we'll look at finding that and imagining things rotating about that. And we're going to cross that angular velocity with the radius from the known point to the unknown point. Okay, so let's start by writing our unknown in terms of its components. So we've got a total magnitude v sub b in one and only one direction. Point B scoots along the floor. It only has motion in the I hat direction. We're also pretty sure it's going to be positive. We can express our t as negative 2 feet per second j hat. It's only sliding down the wall. It's not pivoting out from it. We don't know theta hat. We know that it's pointing in the k hat direction. We don't know if it's positive or negative. And we can define r from t to b by the geometry of the problem. So we have 30 feet sine theta downward in the j direction. And we have 30 feet positive from t to b in the I hat direction. So now we're just going to do our cross product. So we'll end up with a theta hat times 30 feet cosine theta times k hat cross I hat. You're going to get real good at doing these cross products. So k hat's pointing out of the page. So I can stick my fingers out of the page and I'm going to curl my fingers into the direction to the right of the I hat, and I'm going to find my thumb sticking up in the j hat direction. So k hat cross I hat is going to give me j hat. So I get this term. Then I have theta hat times negative 30 feet sine theta times k hat cross j hat, which is negative I hat. So I end up with a negative times a negative, so I end up with a net positive. Now, just like I did in the kinetics, particle kinetics, I'm going to collect terms and solve for all my unknowns. What do I have? I have one unknown, the magnitude of v sub b, the thing I needed to know, and I have the angular velocity of the ladder, another unknown. So how many equations do I have? I have one equation in each orthogonal direction. So I can collect terms in the j hat direction and give myself a 2 feet per second. Take it to the other side because v sub b doesn't have a j component, and equate that to the 30 feet cosine theta times theta dot. Do some algebra, and I get a theta dot of 0.133 radians per second. This is always going to be in radians, not degrees. So if your calculator automatically converts, make sure you do A10 of 45, and if it gives you 1, you're in degrees. So you might want to switch to radians if you're having to do some trig or convert back and forth as needed. If you get a bizarre answer, that may be one place to look. So we know theta hat, and we know it's positive. So that kind of makes sense if you can just envision this point moving down and that point moving out. You would kind of expect a counterclockwise rotation. So a positive theta hat means counterclockwise. So that's kind of an internal head check. We can collect the I hat terms, and that's where we're going to get the magnitude of our B velocity, and we end up with 3.46 feet per second. So we now know pretty much everything we would want to know about the velocity of those 2 points, and we also know the angular velocity of the ladder that's resulting from that motion. We don't know what's causing the motion, although gravity gravity probably is our number one candidate. Okay, let's try another application of our rigid body planar motion 2-point velocity comparison. So in this case, we've got a rod in some kind of machine, and we have a piston that's moving in a straight line with a known velocity, and then the other end of this rod is hooked to like a pulley, some kind of bearing. So it's attached to a bearing which is running in a circular race. So as the piston advances, it pushes the rod, which then pushes on the bearing, and it allows it to move upwards and in its position along this circle. So we have some restricted motion at each point, and so we're going to be asked at an instant in time. So again, we're talking about an instantaneous situation. At the instant shown in the figure, well, at that instant, the point B is at a position that corresponds to this 45 degrees from horizontal. So that relationship is going to allow us, along with the rod length of 5 meters, to get some kind of idea of what our geometry of our positions and velocities are relative to one another. We're going to break things down into their component directions with a coordinate system. And we are given the 53.1 that corresponds to the rod and the 45 degrees. Okay, first step, coordinate system. So we're going to put I hat in the shown direction of A, the VA, and then what looks to be vertically upward is our J hat. So with those two established, counterclockwise rotation is going to be positive K hat, clockwise rotation is going to be negative K hat. Okay, so let's write out our relationship. Velocity of the point we want to know equals the velocity of the point that we already know, plus the angular velocity of the rigid body that they're both sitting on in the planar normal unit vector direction of the plane that they're moving in, crossed into the radius vector from the point whose velocity we know to the point whose velocity we don't know. Now we just have to fill in the blanks. Okay, we know the direction of the velocity of b, and that's the instant in time. That's where we pull in this 45 degrees at this instant. Instantaneous velocity. So we got to think like we're calculus students. At that instant, this point is heading right this way. It is tangent to this circle at that point. So we know that that velocity has a component of 45 degrees in the I hat direction and 45 degree or cosine 45 in the I hat, sine 45 in the j hat. Since 45, they're the same. So we know the direction of VB, but we don't know its magnitude. Nonetheless, we've now gone from two variables that we could have had on this side to just one. That's pretty nice. We know the velocity of A. In this case, it's 2 meters per second I hat. And we can write an expression for VA to B using the rod length of 0.5 meters and our 53.1 degrees. So now all we have to do is collect terms and solve for the two unknowns. We don't know VB and we don't know theta hat, but we have this equation that includes two orthogonal directions, so we have two equations, two unknowns. All we have to do is solve for them. So we collect I and j hat terms and solve individually for theta hat and VB. Just work through the math. It's all algebra at this point. And we end up with a rod angular velocity of 2.86 radians per second. Again, this is positive, which would indicate that it's moving, effectively rotating clockwise around some axis. And that VB is positive 0.12, so it's moving in the vector direction shown. It's moving upwards. If this had been negative, it would have indicated that actually it was B was moving kind of down the circle. Kind of makes intuitive sense. So that's an example of deploying I'm on a rigid body, I'm moving in planar motion, I know the velocity of one point, I want to know the velocity of any other point. And I'm relating them by the angular velocity of the whole body, rigid body, relative to some fixed reference frame. And I need to know the relative positions of my 2 points within the rigid body. Okay, that is it for this lecture, and we're going to continue with more discussions of rigid body velocity, and then start looking at taking another time derivative and seeing how things accelerate in upcoming videos.